It's okay to sit up front, folks. There you go.
Okay, we have our speaker tonight is the University of California, Los Angeles astrophysicist, Dr. Dakotah Tyler. You may have read his article in the March 2025 issue of Scientific America, which highlighted his work. His study of exoplanet demographics focuses on how the variety of exoplanet types distributes themselves around the stars. And Dr. Tyler, thank you for being here.
Absolutely. Thanks for that intro. Can I go ahead and share my screen?
Yes, go ahead, please.
All right. Can everybody see this?
Yep.
Yes.
Cool. Yeah, nice to meet everybody. I am Dakotah Tyler. I actually just defended my PhD last month at UCLA. So I study the evolution of close-in exoplanets, so extrasolar planets, planets that are orbiting other stars. And today I'm going to talk a little bit about that. What we have learned about the population of planets that we have been able to detect, and how they tend to evolve, and how that evolution explains what we have been able to observe. So a little bit about me. First, I have a little bit of a non-traditional background when it comes to astronomy. I grew up playing football. That's all I was kind of interested in. I never really had a yearning for the cosmos when I was younger. Just wanted to go to the NFL. I ended up playing at the University of Kentucky, and I had a couple serious knee injuries, which caused me to, look for something else to do in my life. It was around that time that I started watching astronomy documentaries, specifically the reboot of Cosmos with Neil deGrasse Tyson. And then I went back and watched the original with Carl Sagan, and I was pretty much hooked ever since then. I decided to go back to school and go the physics route, and then ultimately go on to get a PhD in astrophysics. But what I was always interested in was planets, this idea that there were all of these other planets out there. And for some reason, when I first started learning about them, I thought that there were kind of no rules. Like there could be a planet that was all gold and a planet that was made of silver or diamonds. And obviously I didn't really have an idea about the physical mechanisms that go into planet formation, but I have since learned that an all gold planet is, I think, not in the stars for our universe, at least, not with these laws of physics. So exoplanets, extrasolar planets, the ones I study are ones that orbit other stars, but of course there are also rogue exoplanets that have been ejected from their solar systems, and maybe some that just form without a star to begin with. It's not really clear whether or not that's possible, but we know about almost 6,000 exoplanets so far, and we have a bias towards large and close-in planets, and I'll talk a little bit more about that later. But first, I want to bring up an interesting figure. In my opinion, the first, I wouldn't call him an exoplanet researcher, but I would call him an exoplanet visionary. And this is Giordano Bruno, who in the 1500s was quoted saying this: "There are countless suns and countless Earths all rotating round their suns in exactly the same way as the 7 planets in our solar system." Of course, this is before they knew about Neptune. "Their planets remain invisible to us because they are smaller and non-luminous." And I think that this is a remarkable insight for somebody who had absolutely no scientific reason, no observations, no evidence at all to think this, because this is exactly right. the other stars do have planets, and they are invisible to us because they're small and non-luminous. And of course, for his visionary premonition, Giordano was executed for heresy by the Catholic Church. And on his tombstone, or perhaps on this statue, actually, he has another quote that I like: "Take comfort, for the time will come when all men see as I do." And yeah, he was about 400 years ahead of his time, but Giordano had it right. So I like to dig a little bit into the background of exoplanet discovery because it really sets the stage for what we have been able to learn. If you start with our solar system and a general principle in astronomy, it's safe to assume that you're average, right? Like it's safe to assume that we probably orbit an average star, we're an average planet. The Milky Way is an average galaxy. If you think about a normal distribution, you have a very high likelihood of being somewhere around the middle. You wouldn't necessarily expect that you're a special case. Although we do tend to think of ourselves as pretty special as humans. And when we first started looking for exoplanets, this is what we thought that we would find. We thought that we would find other rocky small planets that are close to the star, and then larger gas giants that are further away. And you can sort of intuit why that would be the case. Planets that are farther away are going to exist in regions in a disk around a star where what would be a gas in closer in the disk could condense into a solid. So, having a cubic meter of CO2 gas or methane gas and a cubic meter of CO2 or methane ice, you're going to have significantly more material packed in with the ice. So naturally, you should be able to build larger planets when you get further away. A larger planet, more gravity, can eat up more gas, get more massive, and you can get this runaway effect. And so this was the conventional way that we thought that solar systems would look like, other star systems. And I guess another thing to point out here is how orderly our solar system appears to be, right? You got the four small planets, the four large planets. They're spaced pretty evenly in scale as you go out. Pluto, of course, throws a bit of a wrench into that. It's not really falling in line with the pattern of the other planets. It's much further out. It has this inclined orbit. It has a greater eccentricity, and it's very small and like 50% ice. Of course, there was a elegant solution for that. We just say that Pluto's not a planet. That's why it doesn't fit in with the other planets. But for the rest of this talk, when I talk about Earth-like planets or super Earths, I'll be referring to small terrestrial worlds. The gas giants, of course, are specifically Jupiter and Saturn and not Uranus and Neptune. These maybe we'd call Neptunes or ice giants because they tend to have higher composition percentage-wise of ices like ammonia, methane, CO2, whereas the true gas giants are really dominated by hydrogen and helium with only trace amounts of those other ices. And this just because of the sheer gravity that they have. And here's that snow line that we, at least at the very beginning, thought would be a definitive break between rocky worlds and gas giants. Then, of course, in 1992, the first exoplanets were found orbiting a pulsar, which is a collapsed star, or it's the remnant of a collapsed star that goes supernova. And that was interesting because I don't think anybody thought that exoplanets could exist around a pulsar. You think about a supernova explosion and what that means for the immediate environment. It's hard to imagine that a planet could survive that. However, it is possible that planets could survive it. It's also possible that maybe there's like a second round of planetary accretion when everything is destroyed. there's still a bunch of heavy metals and heavy materials. Perhaps sometimes after a pulsar is created, planets could recoalesce. At any rate, there haven't been that many pulsar planets found. So it's a bit odd that we found them before we found anything else. Then in 1995, we find the first exoplanets orbiting a sun-like star. So not a collapsed star, but a proper star on the main sequence. And this was a shock because we don't see this in our solar system. And this does not align with how we think of forming a gas giant, right? How could you, if you need this incredible amount of material, of heavy ices, etc., that you can only really find beyond the snow line, how could you form a hot Jupiter right next to the star? It kind of defies the way that we thought about planet formation. And a lot of research has gone into understanding these hot Jupiters since then, but ultimately, it's still not set in stone. It seems like there could be a couple of ways that hot Jupiters form. The first one is the way that we said in the beginning, ex situ formation. So you just imagine this massive planet towards the outer edges of the disk, or at least far beyond the snow line. It grows more and more massive, collects all of the primordial hydrogen and helium, and over time, for one reason or another, ends up migrating inward. So, through interactions with the disk, through interactions with other planets, it could get set on a more eccentric orbit. And when that happens to a really massive planet, ultimately it's going to end up dissipating some of that energy through tidal interactions with the star. And over time, what you'll end up with is a hot Jupiter that has basically shed enough of its momentum to end up on a circular orbit that's relatively close to the stars. So this would be a typical migration. Another way that I think was helpful for me to understand why large planets may tend to migrate inwards is before the disk disappears, you just think about a planet that's plowing through a disk of material. It's going to get slowed down. And what happens to an object that's orbiting when you slow it down? It's going to tend to migrate and spiral inwards. In contrast, if you were to speed up an object, it would get a wider orbit. However, there is some evidence that hot Jupiters may be able to form close to the star. And it's possible that there's two formation pathways for these hot Jupiters. So forming far away and migrating in, or just forming next to the star. I think that the migration makes a little bit more sense. It's probably more common, but it is not decided yet. So after we find the hot Jupiters and start to come up with this idea that they're probably migrating in, it kind of seems difficult to imagine that there are a lot of small planets that are close to their star, because if the migration process is so efficient for hot Jupiters, surely this would just cause smaller planets to basically fall into the star or get kicked out. But as we analyzed the Kepler data set, we realized that, in fact, the most common planets in our solar system, or I'm sorry, in our galaxy, are in between the sizes of Earth and Neptune. So they are small planets, and they have relatively close orbits. The key stat from the Kepler survey that interests me is that most sun-like stars have a planet between the size of Earth and Neptune and on an orbit shorter than Mercury. So, balance of probabilities, you pick a random star in the sky, it's got a super Earth or a sub Neptune that's orbiting less than 80 days. And that's pretty interesting because we certainly don't have anything like that in our solar system. We've got Neptune, which is a classic ice giant. And of course, we have Earth, the largest of the smaller planets. But it seems like the most common planets in our galaxy, and there is some detection bias which we can account for. So we should still trust the common occurrence of the mini Neptunes and super Earths. But the caveat here is that it's quite possible that Earth-sized planets or even a Mars-sized planet is the most common planet in a system. We're just not sensitive enough to find those yet. So we can't say anything about that. We haven't completed that part of the survey. But we can say that most systems do have a mini Neptune or a super Earth. And it's not clear why we don't. One reason is probably Jupiter. It seems like a massive planet like Jupiter does a lot to control, and it's sort of the invisible hand that guides what a system can do. And I think that you can build a pretty fundamental understanding just based off of general planet formation principles to understand why that is. You imagine that a disk is relatively uniform. So, it's not, there's different stuff in different locations, but just paint this simple picture that you have a pretty uniform disk. There's going to be some areas where things start to clump up. And then those things start to collide, and some of them break up, but some of them stick together, and then they have a little bit more gravity and they attract more stuff. And it's easy to see that if you just have one area that gets started a little bit quicker than the others, it'll start to dominate the region. And this is what happened with Jupiter. This is how we know that Jupiter is the oldest planet in our solar system. It's the one that got started first. And as a planet grows, a planet like Jupiter, it will suppress the growth of other planets. So having a Jupiter-sized planet where it orbits could absolutely choke off the ability for the flow of material to other planets that are forming. So you imagine that Jupiter is growing larger and larger in the gas disk, and there is some planet formation that's happening in the inner solar system, but you're not able to have like an influx of material that falls towards the inner solar system because it just runs into Jupiter. And what you would expect to see then is a inner disk that has a small planet next to the star, because of course the star itself is a force to be reckoned with, and then a small planet closer to Jupiter, and then two larger planets in the middle. You could really, really understand that configuration by a planet that is gravitationally dominant on one side and a star that's gravitationally dominant on the other, and then a lot of the material kind of that makes it is there in the middle. So we get the Earth and Venus. So that is a possible explanation why we don't have a planet like this, a super Earth or sub Neptune in our solar system. It's not totally clear. It's also still not totally clear just how rare our solar system is. And I'll talk a little bit more about that later, but it just has to do with our detection bias. It's hard for us to detect planets like Earth and Mars and Venus, and even smaller gas giants that are farther away, like the ice giants, Neptune and Uranus. So with everything that we have found so far, again, it's around 6,000 planets, and most of them, not all of them, but most of them are represented in this contour here. So the contours just represent an occurrence density, and it's a little bit easier way to see where planets tend to fall. On the x-axis, we have orbital period in days, and then on the y-axis, we have the size of the planet in Earth radii. So specifically size and not mass. And I want to build out this demographics plot a little bit so we get a better idea of how what we found relates to what we know about our own solar system. So first, I'm going to throw up the radius lines for various solar system objects. You see Earth is way down here, so most of the planets that we're finding are larger than Earth. Neptune right there. Most of the planets that we're finding are also smaller than Neptune. And then you have Saturn and Jupiter, and there's a little distribution. There's a spread of objects up here, a little bit more Jupiters than Saturns, which is interesting. And it's kind of sparse in between Saturn and Neptune. Add another reference line here for the orbit of Mercury, which is 88 days. So again, you see that most of the planets that we're finding are inside of the orbit of Mercury. We'll label the hot Jupiters here, which are a distinct class of planets, and about 1% of sun-like stars have a hot Jupiter. So not extremely rare, but certainly not common. Then we have the super Earths and sub-Neptunes or mini Neptunes. And last but not least, the hot Neptune desert. So you can kind of see that there's a bend in this distribution right here in this parameter space where you get a lot of super Earths that are on 1 to 3 day orbits, and you get some hot Jupiters that are on some 2 to 3 day orbits, but there doesn't appear to be many Neptunes or sub-Neptunes. And that's interesting. That's telling us something about how planets must be evolving. One more thing I want to add to this is called the radius gap. I'm sure you noticed that the super Earths and sub-Neptunes are split. They seem to fall in either category, a super Earth or a sub-Neptune. And that's interesting because why would nature preferentially create super Earths or sub-Neptunes, but relatively few in between? We call this the small planet radius gap. So my PhD research was investigating what physical mechanisms carve this distribution. Strip the exoplanet demographics plot of hot Neptunes and split the sub-Neptunes and super Earths right down the middle in that way. And the main driver is something called photoevaporation. So this is effectively evaporation driven by photons coming from the star, photoevaporation. You imagine a really young star. They spin much faster than older stars do. And over time, they spin down. So the sun is now spinning much slower than it used to. And that slowing of the rotational period calms the star down in XUV output. But a very young star is going to be very magnetically active and very bright in the XUV, XUV and extreme ultraviolet. So you imagine a young star within the first couple 100 million years, still has a bit of a disk around it, and there are planets that are forming. Now, the planets, even the gas planets, they start with rocky cores, right? Like you get dense materials together, and that's how you get the planet forming process started. So you can imagine a bunch of these little rocky cores that have accumulated hydrogen helium envelopes. Even a young Earth would have had some hydrogen and helium around it. It's long gone now, right? This is not what comprises our atmosphere, but a young Earth that was still embedded in this accretion disk would have these things. And you could think about the scale at which that hydrogen helium envelope stopped at something called the Bondi radius. And this is the furthest radius from a planet where a thermal gas, so some gas that has thermal energy, can remain attached to the planet and not be lost to space. So as the star continues to put out XUV, it'll bake away this disk. The disk will evaporate. And once the disk evaporates, the XUV keeps on coming, and it kind of goes for these envelopes next. And you have, like I said, this Bondi radius that is encasing all of the hydrogen and helium around a planet. And the XUV photons are going to penetrate into that, and they're going to start heating things up, right? You're just energizing this gas. And what happens to gas when you heat it up? It expands. And when it expands beyond that Bondi radius, it'll be lost to space. The planet simply doesn't have the gravity to hold on to that atmosphere. So it gets lost, and then over time, it'll end up shrinking because the Bondi radius then is going to get smaller as the planet loses mass through its atmosphere, and eventually you're left with a rocky core. So this is the picture of photoevaporation. Now, here I have an animation. Let's see if there we go. Here I have an animation that's going to show a 300 million year time lapse for a bunch of young planets that are just being born right now around various stars. Here on the y-axis, again, it's the Earth radius, planet size and Earth radius. On the x-axis, we have the period in days. You can keep an eye here on the size of the planet compared to the time. There's going to be a 300 million year animation. And you can think of the brown as the rocky core, and then the blue as the hydrogen helium envelope. So just keep an eye on what happens as time goes on. The envelope shrinks, but it's not completely lost. The planet continues to descend down this radius track, and after about 300 million years, the process slows down to the point at which the mass loss is no longer significant. So right here at the end, the star really starts to calm down. It's not putting out enough XUV to drive serious mass loss. So this planet ends up holding on to its atmosphere. When we look with our telescopes and find this, we call it a subneptune. You could easily imagine a planet that started right here that was much less massive, that had a smaller core, and therefore had a harder time of holding on to that envelope. That would be maybe some of these planets down here. And what do? They quickly drop past that radius gap, and that's kind of the point of no return, where you just don't have enough mass to hold on. So through just understanding photoevaporation, you can start with a distribution of planets that's pretty evenly spread, that isn't sequestered into these two categories, and just press play, let the star do its thing. And depending on the initial mass of the core of that planet, it will either, in the first 300 million years, lose its atmosphere and become a rocky super Earth down here in this bottom population, or it'll hold on to it and be a subneptune. This also explains the hot Neptune desert, because really gaseous planets that aren't massive enough, they just quickly have that primordial atmosphere evaporated away. Hopefully that makes sense. You just think about how massive is the core of this planet and how close is it to the star. Those two things work in tandem to either help a planet hold on to that primordial atmosphere or lose it. So we could picture, a group of young planets that, if we were to look when the system is 10, 20, 30 million years old, seem to be larger. They kind of seem like they're in between this Neptune and Saturn size. And when we look again, after the system is mature in a billion years or so, the planets have descended the radius track, and they're either subneptunes or super-Earths. And this is what we see. A lot of the systems that we see, and there isn't a lot of young systems, which should make sense from a statistical standpoint. If stars live to be 10 billion years old, what are the odds that when we created telescopes, we're going to catch them in that first 100 million years? Not good. So there's there's a handful of these young systems that we know of, and they do indeed tend to have planets that are larger than what we would expect. They kind of have low masses, but large sizes. Sometimes we even call these planets super puffs. They're like the size of Saturn, but the mass of only a couple Earths. And it's kind of surprising. It's not what you would expect. So these are the kind of planets that I try to study, gaseous planets that are undergoing mass loss. Now, it's hard to capture young planets in this process. But we should be able to capture a hot Jupiter undergoing the same type of mass loss. A prime candidate for a planet that is losing its atmosphere via photoevaporation is going to be a gaseous planet that's orbiting close to the star. And it's so massive that it'll never lose all of it, right? So we can kind of cheat a little bit and watch this mass loss process over the course of a planet's life. And this was one of my first research projects, was observing a transit for a hot Jupiter called WASP 69b. This is a 2-scale diagram. The star is a little bit smaller than the sun, about 80% the mass and size, a little bit older, about 7 gigayears. And the planet is 10% larger than Jupiter. However, it's only 30% the mass, which means that this thing is extremely inflated. And of course, this should make sense because it's on a 4-day orbit. If you were to take Jupiter and put it on a 4-day orbit, it would expand greatly, start losing its atmosphere as well. So I got observations using Keck and NIRSPEC, which is a near infrared spectrograph on Keck. Keck is a 10-meter telescope on top of the dormant volcano in Mauna Kea in Hawaii. And what we did was we just looked at the planet, watched it transit, but looked at it at the specific wavelength of helium. These gas giants are primarily going to be hydrogen and helium. So, we can't see them. They're too small and too far away. However, we should be able to see activity in hydrogen or helium. A lot of the hydrogen Lyman alpha stuff is hard to observe because hydrogen in the interstellar medium can mess with your observations. The Earth has a UV cutoff where it kind of eats up Lyman alpha photons as they come in. So it's a little bit easier to observe some helium features in the infrared because they make it through the cutoff from Earth's atmosphere. And I want to explain this plot a little bit because it's a lot to take in. So on the x-axis, we have the wavelength. So the helium feature that I'm looking for is called helium 10830. It's a helium triplet. That's what these 3 dashed lines represent. So this is what we're looking for. We're looking for the helium, which should be coming from the planet. On the y-axis, we have time since mid-transit. So at 0 here is when we expect the planet to be directly in front of the star. The white lines that are horizontal represent the contact points. So the transit starts at T1, ends at T4. Okay. Now, what we want to do is detect variability in helium, which we can attribute to the planet and not the star. Stars also have helium in them. So we want to find a way to normalize out whatever helium is doing on the surface of the star. And a good way to do that is to just stare at the star before the transit starts. And you can see we got about an hour and a half of observations before the transit started. So we can take all those observations and create this master template where we say, this is whatever the star is doing. And from there, we can compare each observation to that out of transit template. And that's what I'm doing here. The color bar here represents variability in helium by percentage. So the darker areas, closer to 1, are going to be the helium looks like it's doing whatever the star was doing. And then as you get brighter, you're seeing absorption from something. Of course, this should be the planet, right? So this bright absorption here is literally helium that is rushing away from the planet. And we're able to estimate mass loss rate of 6 times 10 to the 9 grams per second. So, this is like 200,000 tons per second of helium that's escaping. And this equals, 200,000 tons of material altogether. we can use the helium and assume some amount of hydrogen just by the primordial helium hydrogen abundances. And it equals about an Earth mass per billion years. So every billion years, WASP-69b apparently is losing about one Earth mass. But, it's an extremely massive planet, so this, over the course of its life, still won't cause it to get totally stripped. Now, here I've shifted things into the planetary rest frame so you can really see what's going on. If there were just a bubble of helium that was outflowing symmetrically even around the planet, you would expect the bright spots to kind of hug these two dashed lines. That's the deepest part of this helium feature. But what you can see is that the bright spots are leaning to the left. They're leaning blueward. They're being blue shifted, which, means that they're racing towards us. So in fact, this helium is not just, outflowing evenly around the planet. It's being blue shifted, and it's accelerating in its blue shift as the transit goes on. And when the planet is no longer transiting, we still get an intense absorption and blue shift, which was a pretty interesting discovery to make, because it suggests that there's this long tail of helium coming off of this planet, similar to a comet. So this is a 2-scale diagram that I made of our observations. And you can see this red dashed line is basically where the planet was when we took our last observation. I think the sun came up, so we just couldn't see the star anymore. And we still detected helium that was in front of the planet, in front of the star. So this equals about 7.5 planetary radii. So this planet has a tail that is at least 7.5 planetary radii. Pretty remarkable. You can see the top-down view, the bird's eye view here on the right, where the tail is escaping and being accelerated towards the observer. This should make sense because there is a stellar wind. There's material coming off of the star. And as the tail is, floating and trailing behind the planet, it's getting accelerated by the stellar wind from the star. Now, this was a pretty interesting discovery because this planet had been observed before, and there didn't seem to be evidence of a strong tail, of a really long tail like this. So we had our work cut out for us in the interpretation, trying to explain exactly what was going on. In this panel at the bottom, I have included some 3D simulations from a theorist that does work on exoplanet atmospheres and how they interact with stellar wind. So in case A here, you have a hot Jupiter that's orbiting a star, and there's some stellar wind strength. The exact amount doesn't really matter. But in panel B, what they do is they turn the stellar wind up by an order of magnitude. So they make it 10 times stronger. And you see that you start to sweep away a lot of that helium. It can't just float around in a torus around the star because the star is, blasting it away. And then in case C, they turn up the stellar wind strength by an order of magnitude again. And here I think we can see exactly what's going on. This looks remarkably similar to the overhead case here, the bird's eye view of what we saw in our observations. So this could be explained by a star that just has a really strong stellar wind and is sweeping the material back into a tail. It's basically what's happening with comets, right? A comet gets a little bit too close to the star. The gas starts to vaporize. Some of it leaves the comet, and then as it encounters the solar wind, it gets blasted back into a tail. So very cool. Here's an animation that was made for the press release, and here I think it's just cool to see what exactly is going on in this system. You've got the star, that's got a decently strong stellar wind. And then we see the transit, we see helium escaping, and then we continue to see helium for at least 1.5 hours after the end of the transit. Some interesting stats from this tail. It should be something like 10,000 Kelvin. So it's extremely hot. The gas is accelerating towards us at about 23 kilometers per second, which is really fast. So, this is a chaotic and violent environment. And that 7.5 planetary radii can be converted to 350,000 miles. Now, I said that this system was observed before, and that really is why our observations were so interesting, because the group that observed it before did not see this significant tail. The two plots on the left are essentially the same style plot that I showed you before, where you're just looking at the relative variability in this specific helium band over the course of an observation. So when the group observed this, they did see helium, so there's mass loss going on. That's good, but they don't really see a tail. I think they saw excess absorption for about 20 minutes. Compare that to the 1.5 hours that we saw it, then you may think this planet, sometimes it has a tail and sometimes it doesn't. That's weird, right? It's orbiting the same star. It's orbiting at the same orbital period, right? So 3.9 days. Why would it be having a tail that is appearing, disappearing, and reappearing? This just doesn't really make sense. So very cool discovery. I ended up presenting at the breaking press conference at AAS 243. It was really cool. We had an article written about our project in the New York Times, hopped on the Canadian broadcast channel and Australian broadcast channel Science Podcast. So it was very cool to talk about this. And then I think the crowning achievement was getting a clickbait headline. Somebody converted the tail length to Mississippi rivers. So scientists find a planet with a tail 150 times longer than the Mississippi. And I didn't believe that at first. It didn't sound right to me because it doesn't sound long enough, right? We're talking about planets in space. But I did the math, and 350,000 miles is about exactly 150 times the length of the Mississippi River when it's straightened out. So I have to tip my hat to the journalists for doing the conversion right, at least. I don't know how helpful those units are, but the conversion is correct. So what we really want to be able to do is not just say, hey, we found this cool thing that was a big surprise, but to be able to explain why. Why did we see this? Why does this planet now have a tail, but didn't when the observations from not even a year prior were taken? Like, how do you explain that? You wouldn't expect that significant of variability in a star planet system on a short time scale. Like maybe over tens of millions or hundreds of millions of years. So you really wouldn't expect that over, from June one year to July the next. Well, you're probably familiar with the fact that our sun has a solar cycle, has magnetic activity cycle. Right now, it is pretty active, and that cycle for the sun lasts. It's slipping my mind. I think maybe 11 years, somewhere around there. And you can also study the thermosphere of the Earth. So this is the upper atmosphere, think really high altitude. And you can, study the thermospheric power and plot it against the solar cycle of the sun. And what you see here on the left is that the activity in the thermosphere of the Earth traces the solar activity cycle, which tells us what? Well, probably tells us that you can, by proxy, determine what the star is doing by studying the upper atmosphere of the Earth. It's interacting with whatever is going on with the sun. So, if this is true for the Earth, we've got to think that it's true for other planets. And, we don't even really have a significant atmosphere. If I found an Earth-like planet with the current technology and techniques that we use, I would tell you this is a stripped rocky core that doesn't really have much of an atmosphere at all, right? Our atmosphere is significant to us, but it's really paper thin. And if you've ever seen an image of the Earth in space where sunlight is kind of hitting the edge, then you see it. Like we have a very, very, very paper thin atmosphere. So, what about a planet with a much more significant atmosphere? How does this thermosphere solar activity relationship look for a planet like a hot Jupiter? And a collaborator that I work with, who also has been studying this planet WASP 69b, was interested in this same phenomenon. It's like maybe what we can do is we can try to trace somehow the stellar activity by looking at X-ray activity and see what the tail, what the atmosphere of WASP 69b is doing relative to the star itself. So we've been able to populate a few observations. We've used a number of different instruments, so it's not always a one-to-one comparison, but I think that this is really interesting in that essentially what we found with this planet is that it behaves like a windsock that is catching or going limp based on the strength of stellar wind that's coming from the star. So this is sort of like the first time that this I guess this is a technique. It's the first time this technique has been used to probe the activity of the star itself. It's really interesting. And the only way that we'd be able to prove this is to get more observations. And I think that the reason this hadn't been discovered yet is because you know what scientists want to do, what researchers want to do is they want to find something new, and if there's not anything new and like not any interesting publishable data or potential, then they move on to the next thing. So I think what were doing where they were getting single observations of these hot Jupiters and trying to see if there's mass loss happening, and they either see it or they don't. They see a tail or they don't. They see a spherical outflow, whatever it is, and they just move on, and nobody looks at it again. Which is this interesting, not to get on a tangent, it's this interesting thing about science where things should be reproducible and you should be able to continue to validate them. But from a scientific perspective, you're incentivized to just find something new and not repeat work. We ended up looking at this system that had already been observed and found something interesting. So we're going to continue to observe this. We got more observations at Keck. Here I am observing at the UCLA remote observing facility, just internet dialed into, connected to the telescopes at Keck. I think this was last summer. And we ended up getting observations with the same instrument of WASP 69b again. And the two panels at the bottom are the new observations. The two panels at the top are the ones that I showed you earlier. So a reminder, on the right, we have everything shifted into the planetary arrest frame. So, this is what you'd see if you took your spectroscope from the planet and, moving in the planetary arrest frame. And then the one on the left is the stellar arrest frame. And you can see that there's definitely still helium. So this is like an ongoing analysis. This paper has not been published yet. But there's absolutely still helium that is escaping from the planet. However, there does not appear to be any tail. So, I mean, this is, again, it's really interesting because the way that I think about it is that the theory here for how planets are having outflows that are sculpted by stars, it hasn't really been developed yet. Like there's the models don't exist that can explain this, aside from what I told you, which is this intuitive, the star is maybe getting more or less stellar wind that's associated with the solar cycle or the stellar cycle the magnetic activity cycle of the stars themselves. So this is a super interesting observation. And this is the one I wanted to talk about. I have a couple other ones, but it looks like we're coming up on 45 minutes. Looks like I already passed 45 minutes, actually. So one last thing that I wanted to say. I came out in the beginning and I said that most stars have a super Earth or sub Neptune. They're the most common planets that we find. But I just want to point out that pretty much what we know about exoplanets can fit into this Kepler box here, this red box, where planets that are closer to their star than the Earth and larger than the Earth, we do a great job of sampling. But anything outside of that box, is incomplete. There's low completeness. We just can't detect these things. You can see that we can't detect a Mercury, a Venus, an Earth, a Mars. We can't detect like most of the planets that exist in our solar system. The blue simulated data points are for what used to be called the W1 telescope. Now it's called Nancy Grace Roman. So that instrument will do microlensing observations and should be able to populate some of these more massive and the larger planets. But you think about future telescopes like the Habitable Worlds Observatory, the 30-meter telescope. If that ends up getting built, then hopefully we can start to build out and get a better understanding of where our solar system actually fits into these, to the grand scheme of things. So a lot of exciting research going on in exoplanets, and with all the new instruments coming out, I'm really hopeful that we're going to approach being able to actually find true Earth analogs that are the size and the distance from their star as the Earth is. So thank you for your time. Sorry if I went a little bit over, but I definitely want to take any questions about anything that I said, or anything exoplanets. Really love to talk about it.
Yeah, anybody's got any questions, just ask, and hopefully the mic will be able to pick you up, or we might ask you to come up front. Any questions?
I'll go.
Okay.
Thank you for a wonderful presentation, by the way. Does the Vera Rubin Observatory that's coming online, would that be of any value to your research?
It wouldn't really be any value to my research. It's looking at time domain changes, which will be relevant for people that are studying galaxies, maybe like star clusters, nebulae, but it's not going to be super helpful. I think for the specific type of research that I do, I do think that it has the potential to find Planet 9. I think in a test exposure that they did of 10 hours, they found something like 1,000 or 10,000 previously unknown asteroids, which is remarkable. It'll probably find like all the asteroids in our solar system that we don't know about, which is really important. But what I think is really interesting is that it may be able to detect Planet 9. I don't think it'd be able to see it necessarily because it's so far out, if it does exist, that it's not going to be giving off much light. But then again, the asteroids don't give off much light either. But it may be able to detect the disturbances that it causes. So that's not, directly related to mass loss work, but it is really interesting because it speaks to like early system dynamics and why that planet, which we believe is basically the mass of what a super Earth or sub Neptune should be. So, perhaps we actually do have the super Earth sub Neptune planet, but for some reason it got kicked out into the outer solar system because of Jupiter or like some weird interaction with the disk or one of the planets. So actually, I would say tangentially that is important to the research that I do. But in terms of like mass loss, not really.
All right, thank you. Are there any other questions?
I have a basic question, and
Yeah.
the second, if it's okay. What's the radius of the sun versus our sun versus Jupiter?
the radius of our sun versus Jupiter, I think our sun is something like 10 times the radius of Jupiter.
Okay. And second question, I'm assuming you'll be continuing to observe WASP 69. How
Yeah.
frequently is it being observed?
That's it depends. So far, we're kind of hitting it at a cadence of a couple times a year. You need the observation to kind of line up perfectly with night and telescope time that you can actually win. So I think we're hitting it at a cadence where in a couple years we'll be able to reliably make a conclusion about whether or not the atmospheric effects, the mass loss effects that we're seeing, are in some way, at least in morphology, tracing what could believably be the solar activity cycle for that star. Because we're also getting X-ray observations of the star as well using Swift. So we're both observing transits of WASP 69b and getting X-ray observations of the star to try to get an idea of where it's at in its activity cycle.
Interesting. Good.
Any other questions?
Yes, Dr. Dakotah, at the outset, you talked about the rogue planets. Could you speak for another minute about those? Do we have any numbers of how many, what size, and how close?
Yeah. So the estimates vary because these planets are very hard to find, right? They don't orbit stars. They don't give off any light. An Earth size, Earth mass rogue planet would be effectively invisible, to our current detection techniques and instruments. But dynamical simulations show that planets are going to get kicked out of any system. Really, it's something that's very common. In fact, I think it's something that's so common that the estimate is that there are more rogue exoplanets than there are planets actually orbiting stars. So, if you set that as your lower limit and assume that there's at least like one star or one planet per star, 200 billion stars in the Milky Way, maybe there's a couple hundred billion, maybe a trillion rogue planets. And that seems a little bit frightening because a trillion is a large number of invisible planets to just be floating through the galaxy. But if you do the calculation, the planets are so small and still everything is so spaced out that there's effectively no chance of a rogue exoplanet entering the system. With that being said, that is one of the hypotheses for Planet Nine, if it does exist out there. One of the idea that I like is that it is a super Earth that formed in our system and for some reason got kicked out, but didn't make it rogue. It wasn't moving fast enough to escape the sun's gravity and instead ends up on like this 20,000 year orbit. But there are, it's a reasonable hypothesis that could also be a captured rogue planet. It's very unlikely, but I mean, I'm sure that us evolving to use Zoom is also very unlikely. And, here we are.
Thank you.
Yeah.
I also didn't hear you talk at all about TESS. Is there a reason for that? You talk about um, the other Kepler and W first, but you haven't mentioned anything about TESS.
Yeah. No, so TESS has, I've done some research on some TESS planets. I just didn't mention it. A lot of the like core takeaways that we learned about the distribution of small close-in planets came directly from analysis of the Kepler catalog. So I didn't mention it, but there's no reason for it. TESS is going to find a lot more planets than Kepler did. I think that TESS is approaching 1,000 confirmed planets, and there's something like 7,000 or 8,000 candidates right now that are just awaiting confirmation. And as TESS continues on, it's going to start catching, not only confirming more planets, but getting planets that have longer transit time. So planets that are a little bit further from their star. So I just haven't talked about it. But yeah, I mean, test is also really, really important, at least in the discovery, right? Like the instruments that I'm using are for like a closer detailed look at these systems. So the most that I would do with test data is figure out where a potentially interesting planet is.
Okay, great. It's good to hear that it's alive and well and still producing data. Thank you very much.
Oh yeah, absolutely. Question.
I think we're it with the questions.
Okay, thanks for having me. Love talking
Yeah,
about this stuff.
Thank you
Thanks
very
for the
much for the
questions as well.
presentation. Excellent. Thank you.
All right, take care.